Hello, everyone. In the last class, we have already discussed the conditional probability, and we used two examples to illustrate the process. The first one is testing, like the positive and negative testing, using the Bayes rule and law of total probability to figure it out. And one common feature is the probability tree diagram. And the second example is the multi-stage R model. So hopefully you can still remember it. And in this class, I'm going to discuss a more advanced example from conditional probability, the famous puzzle, Gambler's rule. So what does this example means is that imagine there's two gamblers A and B. They play a game of chance over several rounds. For each round, if A wins, he will wins $1 from B. But if he loses the round, he pays the player B $1. And in each round, A wins with probability P, and B wins with probability 1 minus B, which means there's the chance that A wins and B wins are certainly, and if you add them together is 1, but the P is not equal to, it's not, we cannot say it's equal to 1/2, but it's probably 1/2. And combine the capital of both gamblers is K dollars. So they have K dollars combined, both of them at the beginning. And before the game begins, A owns X of the K dollars. And the game stops as soon as one of the two gamblers is bankrupted, which means he loses to 0. So what is the probability that A loses the game, or the gambler A ruins in the end? So firstly, let's explain in a diagram. So we can see here first, it has total amount of K, which means K is the total amount of money that the number of dollar A and B wins together, owns together, and they cannot go beyond this or below this. It stays stable for the whole process. However, A starts with the probability X, as located here. So A has some chance to win the game if he wins, lost, wins, lost, win, and hits the K and A wins. However, if A goes down, then A loses the game. So for each game, A wins with probability P and loses with probability 1 minus P, which is the probability that B wins. Okay, so when we are familiar with the problem structure, we will use our condition probability to help us to solve it. Seems like a very hard problem at first, but we can define some terms here. Like we can say the pi x, or if you are more familiar, like the px or fx is a function that the probability that A loses, or it's a probability function. Like px means the probability that A loses, but we use pi denotation here, and x is from 0 to k, which means that's the probability that A loses starting with the unknown of X dollars. And RA here we define is an event that the game leads to A's ring. So A loses the game if RA happens. So there's two outcomes for each round. So WA means the event that A wins the first round, and WB means that B wins the first round or A loses the first round. So based on the conditional probability, imagine we are already finished the first round. So there's only two outcomes for the first round, like whether A wins or B wins. So now we're considering the second round. The second round is there's one probability that A wins the game with P times the conditional probability that the second round that A loses game depended on condition on A is already win the first round, and plus the probability of A will ruin in the end, given that B already win the first round. So it will times the probability that B wins the first round, which is 1 minus P here. So we use the we use the law of total probability because we know we know whether it wins or lost. So there's two subsets of the first round, A wins and B wins, and we combine them together using the addition between them. So this is and this will somehow simplify the problem because if we only know that for the first position, so it is here, and we are not sure what goes on to here. So now at least we solve one, but there's more probability as it goes more in the process. So we are simplifying as we reduce one step beyond, and we get a longer formula. So this is a successful illustration of the conditional probability in the realistic problem. And okay, so as illustrated before, the probability of RA given by WA is A wins the first round and A's capital increases to x plus 1, and R given by WB for the same reasoning, for the same explanation. So the probability of RA given by WA is equal to pi x plus 1 because okay, we have one more dollar for A's for the condition here because WA is already wins one, so A already wins one, so we plus 1. So for the second condition, if B wins, then it's equal to pi x minus 1 because A already gives $1 to B. So we can form a new formula here based on this one. So PRA, the probability RA happens is definitely pi x. So pi x is equal to P times pi x plus 1 plus Q, which is 1 minus P times pi x minus 1. And this is the second order linear difference equation. So how can we solve this? Because based on this question, we already know like the pi zero is equal to because imagine if it starts with 0, then he will definitely lose the game because he will already lose the game, so it's equal to 1. And if pi think of pi k, or pi k, so if A starts with k, he already wins the game. So the probability of pi k is equal to 0. It will never wins the game, and pi 0 is 1 because he will definitely lose the game. So this is the two conditions that we'll use to solve the multi-stages of this explaining and expanding. So let's consider third term. So third term means this probability will still times some more complicated condition, like in the second round it wins and loses, so it will become longer and longer. And believe it or not, it will converge into this one. And this I think when we get this solution from the gambler's ring, we use one definition called martingale. And martingale that's like that's in a graph. So I don't know whether you know the graph, but there are many nodes in the graph, and if it moves from one node to another node, and all the connection between them are with the same probability. So so in that case, it means if we reach a stationary distribution for that graph, and all of the connections are the same, so it's just like the P divided by Q to the power of the depends on the step it experiences. So this formula is getting from the martingale, and if you're interested, you can search on I believe like Wikipedia is a good source for explaining that, although many people don't like Wikipedia, but or you can search on Google to find out some more useful sources. And yeah, the martingales and the final version or a more detailed version of Gambler's ruins will be discussed in 396, which is not now. But this example is just to give you a feeling of how the conditional probability, the idea is used in realistic problem. So, so here is another it's a advanced problem for solving difference equations. So we just see one linear difference equation, and the lemma tells me if if one first order difference equation is with a not equal to 1 and b, and those are constants, and more importantly, I would say this is an implicit formula, which means the xt plus 1 is dependent on xt. If this is true, then the solution to this one will be this. So xt is, if you know the x0, and you can definitely calculate xt by using this formula, and the proving process is here, because x1 is a times x0 plus b, x2 equal to a x1 plus b, and this step just continues to end. So what can we find? If we plug x1 equal to a times x0 plus b into the second equation, we get a square times x0 plus ab plus b, and this one can be simplified into a square x0 plus a plus 1 b, and x3 we plug x2, we plug this formula into the x2, and we find out this one, and we found out the a to the third, a to the power 3 times x0 plus a squared times a plus 1 times b, and we continue this trend, and we'll find that xt is equal to a to the power of t times x0 plus a t minus 1 plus until 1 and times b. And here we will use one famous formula from mathematics. Is called the how to say, the polynomial difference formula. So so for any 1 minus a to the power of t divided by 1 minus a, so not consider this term, not consider 1 minus a now. So just consider 1 minus a to the power of t. This can be written as 1 minus a times something, and the times something is just this, based on the polynomial difference formula. And so we can simplify this term into this one, and luckily it's just in the lowest part. Is we can convert it to this formula and find out. And the last step is just we extract a to the power t from both of the terms, and you can get from this step to this step just by moving a to the power t out and get this formula, and we are done. So this is one additional problem that I want to discuss from last lecture's material, and the main material for this course is random variable. So what are random variables? So specifically speaking, previously, imagining like all the experiments we meet with, the experiments in probability, they have two characters, whether they are single experiments or they are like multi-stage experiments or they are conditional independent experiments. They can like form a chain of experiments, but we are all discussing the outcome of those experiments specifically. Like for example, if you are playing the poker cards with others, we usually discuss like what's the outcome of three queens, 2 jack, 1 king formed by a 6 card hand. But sometimes we're not really interested in a specific outcome, or like if you flipping a coin, what's the probability that you get a first head, then a tail, then a head, or then a tail? Or sometimes we just want to ask how many heads are there, or like what's the probability that you get 2 heads, or or what's the probability that you get 3 queens from a hand, and from other aspect like how many jacks you get, we don't consider that. So here's the definition of random variables. This helps us to simplify such complicated outcomes into real numbers. So often we are not directly interested in the random outcome W of an experiment, rather some numerical aspects of the random outcome. So first of all, let's the probability space be this one, and the function, we define a function from the probability space to the real number, and we call it measurable if for all alpha belongs to the real number, this is true. So if let's say if alpha is a real number, it can be infinitely large, no problem. It can grow infinitely large, but the core of this definition here is all the outcome from this probability space is belong to some fancy A, which is the power set, or the sigma algebra, right? Remember the definition from the first several lectures, and such a random variable is a measurable function, x from the sample space to R. So any random variable is measurable. And once we know the measurable definition of a measurable function, we can know the definition of a random variable. So more specifically, in discrete cases, in discrete probability, the sigma algebra is always the power set, which is denoted by this denotion. So every function x it grows from the sample space to the range of the whole real number as a random variable. There's no doubt in discrete one. But in continuous one, maybe sigma algebra is not the power set, but or so they may not be measurable. So this is I would say this is more advanced material in major theory, but in this course I would say most of the cases we can still consider continuous probability to be a random variable. So very theoretically it may not happen in that case. We are still on the road to find out, but for now, if it doesn't cause severe lead to the fail of false understanding, we keep this in mind and just use it. So a graph understanding of the random variables, consider this a sample space, and this is specific outcome, and this is a set of outcomes, and it can be converted to some point or some interval on the real line. So mainly the random variable is a function that converts the sample space into the real number, but only some small portion of real number. So more specifically, if we say like the probability of some, if A happens, the probability just goes to what if A happens on the real line? What's the probability of that? So let's see an example to help us understand. So if we toss in a coin 3 times, and we might get 8 outcomes. It can have 3 heads, head, tail, head, and so on. And by listing all of those outcomes out, we can find it has some specific features. It has one case that has 3 heads, 3 cases with 2 heads, 3 cases with 1 head, and only one case with 0 head. So in this case, we can say a random variable converts the outcome of 3 coin tosses into the number of heads that occurs in the outcome. And usually we use the X to denote a random variable, which is a capital letter. And also we can consider random dialing. So consider a scammer who picks and calls telephone number at random in a certain area. So the sample space is, of course, all allowable phone numbers in that area because it will call them one by one. But what's the difference here is that if we say there's only two cases of what will happen to the telephone call, whether it is picked or not picked. So if a phone is picked up by that phone number, we say the XW will be 1, and if it's not picked up, it will be 0. So in this case, we summarize all of the outcome of the numbers of the phone numbers into two cases, whether it is picked up 1 and not picked up 0. So this is also illustration of random variable. And third case is a spatial data. So consider the case that X is the current temperature of a random location, and the sample space is so 0 to 180 is like, I would say better to say -90 to 90 because that's latitude, and 0 to 360 better written as -180 to 180. That's the longitude. So the case is well, if it's written in this case, we'll say it's hard to imagine it's actually on Earth, but we can still say it's on Earth. This is the whole Earth map with the unit of latitude and longitude, and we can use a random variable to convert the location, which is pretty very hard for us to know, to some current temperature at location W, which the W is from this this map, the whole Earth map. So in this case, the random variable convert a certain location to the temperature of current temperature, which is also a real number. But I'll say in this case, if it's not specifically says that we can only know integer temperature or temperature with some decimals, it is continuous one because temperature is continuous. It goes from, like, for example, 0 degree Fahrenheit to 100 degree Fahrenheit, and that's possible, and it can be continuous. Can be any value in that range. And there are some important conventions like uppercase or lowercase. So usually the denotion, like the capital X to W means the X, which is a real is a random variable that assigns an outcome. The W is an outcome, some value, and the small x here, the small letter here, is the value that the function X assigns to the outcome W. So we say X is a realization or observed value of X W, and we open drop W and write X only. So what that means? So because if you imagine it, you write X and bracket W, that be they will use more ink if you written that very frequently, because instead in statistics we definitely write random variables many times. And if you want to save some time, save some hand forces, we'll say, why not just use X equal to something? Because W already know it's definitely outcome and it's not changing. So this becomes S equal to A, and A is the signed value, is the realization. So this actually means for longer term that it means all of this set means all of the outcome from the sample space that has the property, if it's given by the random variable X, its realization will be A. And this is a set means for that too. So clearly this is much more simpler. For example, let X count the number of heads in 3 consecutive coin tosses, then X equal to 2 is equal to HHT, HCH, and THH. Because that means all of the 3 tosses from this set that has the property only 2 only 2 happens. So that illustrates really well with the previous page. And for example, let's say the sum of 2 dice is a random variable. So now we have a new random variable. We want it to represent the sum of 2 dice outcome. So first, let's say what's the sample space. The sample space is like the product Cartesian product, W1, W2. So, and each W here, Wi here can be 1, 2, 3, 4, 5, 6. And the sigma algebra is because it's discrete, is equal to the power set. So this is a measurable function, right? This is a measurable function, and because we define the x1 and a new random variable from omega to r to the real number, it means that x for any given outcome is equal to w1. And we also denote x2 is equal to w2. So the x1 is a random variable that only counts that converts to the two rollings only equal to the first rolling, and the x2 represents the rolling only of the second rolling. And now we say the final random variable x, want to say, is also from sample space to real number, but it's plus the 2 terms together. So it's plus the value of the first row to the value of the second row, and if we add them together, it is equal to xw, which is the sum of the 2 dices. So we are done. And we verify that x is measurable because, okay, we already proved that x1 is measurable, and for second reason, x2 is also measurable, and because they're both measurable, plussing them is also like a discrete distribution, right? It's still discrete. It only has 36 single points to add together. So x is measurable as a final result. And because x is measurable and a random variable is a measurable function, we can say this function here is a random variable. But remember, these 2 terms are not clearly defined. We have to add this line and this line together to say what's the random variable really looks like. And what is the distribution of a random variable? A random variable x defines a probability measure px. Usually we denote the x to the bottom right of the probability. On the real number is by assigning each a belongs to r, that a takes a value in a. So pxa, this donation, you will see it very frequently in later courses, and it's the core of the probability theory. And this notation means the probability that the w happens, the outcome happens, if the random variable takes the outcome belongs to a certain subset of the real number line. So this is actually means p inverse x to the a, because x is convert outcome to a real number. So x inverse means it converts the real number into an outcome. So this actually means the probability of some outcome happens, which the outcome's value, the realization of that outcome is a, is in the set A. We can think of a random variable x as transferring the probability from the sample space to real number. So this is no doubt, and let's say a more precise definition: distribution of a random variable. Let X be a random variable on a probability space omega, fancy, and P. The probability distribution Px on R is defined by Pxa equal to P equal to the probability of omega belong to W belong to omega, X W belongs to A, and A is a subset of real number which is measurable. And we call this distribution of X, the distribution of the random variable X. And so by the notation we learned about here, we say, well, sometimes we don't write this thing out. So this large set can be converted to a smaller set. So which means the random variable is belong to A, belong to some subset of real number. So here there's a note for us to notice. Different randoms defined on different probability space may have the same distribution. So we can therefore hope to reduce the study of different experiments to the study of just a few random variables. So this is easy because like the cases we defined above, the dialing, the phone number dialing problem, that case only have two outcome, 0 and 1, right? And I would say 0 and 1 all have like probability maybe 50 to 50. And for another case, if we are defining the city of let's say city of Boston, the city of Boston, whether on that day whether it's raining or not raining, and if it's raining, we give it 1. If not raining, give it 0, and it's also 50-50. In like not reality but ideal, like 50-50. So the two random variable is the same, but their sample space is different. The one is a whole set of phone numbers in that region, and the second is the whole record of the weather in Boston's history. And the second topic we're gonna discuss today is the discrete random variable. And a random variable S is called discrete if there exists a finite or countable infinite subset D is subset of R such that P X belongs to D is equal to 1. So this is the same as saying there's a finite or countably infinite subset that all of the cases, all of the real numbers that we can find is in that D region. So the probability is 1. There's no probability that it can go beyond D. So and this is the same definition as we from the definition of 3.1, the discrete probability space. And if you forget about that, so try to go back to see that lecture slides and how that definition is, because that is more I believe it's more advanced than this one. So but the logic is just the same. And because we defined the random variable, this distribution of random variable here, we'll say for discrete random variable, which is the same as saying a discrete experiment that we as our lecture before, we can define a mass probability mass function for discrete random variable. So let X be a random variable, and X is in the range X1, X2. So those are the realization of X. X can only be such, can be all of the possibility of a realization of X is in this set. So the function we define P from X omega to R is defined by Pxi equal to the probability that XW's realization is Xi. And this also, by simplification, this means Px is equal to Xi. So for any of the outcome that is equal to Xi, we combine those whole probability together to get the probability mass function of the discrete random variable. And so a function can be continuous or it can not be continuous. And in some cases, and especially in discrete cases, it's not continuous as well. But we can form something to connect them together. That is just to define px equal to 0 if x is not in that D region. It's not in D, so it must be 0 outside. So in that case we can combine them together to get 0, and it's a function that has value for any inputs. And one consequences of this definition is that we can ignore the original sample space when dealing with discrete random variables if we only care about its numerical results. So let's say Px belongs to A. This is equal to the probability of this one. And because we know all of the outcomes for x1, x2 here, they're discrete. If x1 not equal to x2, then xw, if the xw equal to x1, it cannot be equal to x2. So they are discrete. They are disjoint sets. As a result, we can write this step to this step as to separate the union is equal to the summation of all of x equal to xi given by xi, given summing of all xi belongs to A. And this is also true for the summation of xi belongs to A, p xi. This is the definition of the mass function, the probability mass function here. So let's recover the example we talked about before, like the sum of two dice. So let's first compute probability of x greater or equal to 11 using a probability mass function. So probability of x greater or equal to 11, it is because the maximum cases of p, as we can write them out, first x 1 to 6, the second dice 1 to 6, and we add them together, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The maximum case is 12. So there's only two realization. There's only two realization. As we can say, the realization is the xi here. There are only two xi, 11 and 12. That is greater or equal to 11. So probability of x greater or equal to 11 is equal to probability of x equal to 11 plus the probability of x equal to 12. So definitely there's 2, 11, 1, 12, and totally 36 cases. So 2 over 36 plus 1 over 66 is equal to 1 over 12. And that's an illustration of that case. And in addition, the discrete random variable have more properties, just like the probability we defined before for different outcome, different events, different experiments. Random variables have some similar properties, like for each of the xi, the probability mass function of those random variables for those realizations is greater or equal to 1. And if we sum up all of the possible realizations together, is equal to 1. So these two properties are very similar to we discussed before, like all probability are non-negative, and if we sum up all of the events in all of the outcomes, as probability for a probability major is equal to 1. So that's it. And so there's some like proving for why this works. So first, let's prove the forward direction, which is which I believe that if you proving each of the small provings before, you will definitely understand the structure. So first we say by the definition of Pxi equal to P x equals to xi. This is greater than or equal to 0 because, well, Pxi is a probability, and our probability is greater or equal to 0. So this explains why this is true. Notice just one step, and we already know that 1 is equal to the probability of x belong to x of omega, because for the sample space, the x belongs to x of sample space. That means it is the whole case of the problem, so it's definitely 1. And for this representation, we can write as the union of xi, of x equal to xi, the set that xi belongs to the whole set x x omega, which is the whole set of the real number in that set. And this is uses the partially like the partially disjoint events of xi. Then by using because they're like 1 by 1 disjoint events, we say, well, the probability of the union can be written as the summation of the probability, and goes one step more because the x omega can be written as it's the whole set, so it grows from I equal to 1 to I equal to infinity, and this is the power of x equal to x1 to xi. Sum them up, and to plug in this equation again, and we get the probability mass function of xi for the summation from I equal to 1 to infinity, which is the whole set, is equal to 1, and we thus prove this case here. Okay, and I think that's all for today's class. And there's one more page, but this page is I would say it's not very useful. It's just illustrate how to go back. How do you say if p is a function that satisfies this? If we know this, how to prove it's a discrete random variable? But sometimes if we give one more thought, like we already know this two facts, definitely it is a discrete random variable because or at least a random variable, because these are the property. So this page is for those who want to prove for themselves. I would say the proof is at the same level as this one, but it's just nonsense by my sense. Okay, so that's all for today, and enjoy your day for the whole week.